Is we're looking at building the next generation of 40, 50, 60-meter telescopes. And to do that, we have to go to novel ways of doing it with lightweight optics and adaptive optics, and then apertures that are not filled. They're annular, basically. And we've made some good progress with numerical simulations there. We're now starting to build some prototypes for this. But our vision is to actually have telescopes of 40 meters plus. The next thing we're doing in this imaging work is we're actually using our techniques to look for extrasolar planets and imaging them. And we made a breakthrough 2 days ago. In the bottom left-hand corner, it's very poor to see it here, but the state-of-the-art imagery there shows that current techniques can detect about a contrast of about 10 to the minus 4 in 2 seconds of data, and we can beat that by a factor of 5 using our techniques. Moving on to the seismology of the solar system, we go to South Pole, Antarctica, where we take measurements of the Sun and Jupiter and Saturn, and we're using those to look at vibrations set up by sound waves generated in those bodies, and we actually image the inside of those the bodies. So we do a seismic probing and look into the very cores of them. So what we're hoping to do with Jupiter and Saturn is be able to distinguish between the competing theories for how the solar system was formed. In all of this, what we do is we build instruments. So we build instruments for measuring Doppler velocities of the Sun and the planets, and also adaptive optics systems for looking at the satellites. And we've got a lab downstairs where we're building a simulator that will simulate the Earth's atmosphere. And we can take our ideas and test it out once we've got the simulator running. Last but not least, in our group, we've got some really good connections with Italy and the Jet Propulsion Lab and the University of Hawaii. And the students that work in this group, a lot of them have gone to Hawaii now, and they're going to go to Italy. And they've had internships with JPL and also with the Air Force. Am I good? Oh, I've still got 2 minutes. All right, so back up. So one of the pictures that I don't show here that we're really proud of, and it's because I was doing it in a rush last night, which Megan can attest to, because I sent her the wrong file twice, is that we're able to take a picture of a satellite during the daytime, which is like looking at this blank wall. If you saw the picture, there's nothing there. And we can actually extract something that's almost as good as the image of the Hubble Space Telescope on the bottom. This is really exciting because it means that we're opening up the possibility of daytime astronomy, where we can actually look very close to the Sun and image objects all the way up to the edge of the Sun during the daytime. Another area that we're working in is we're building atomic filters for looking at these objects, and we're going to do them in new materials. In fact, we want to do materials that we can actually look at lines simultaneously across the whole spectrum to improve our velocity sensitivity of measuring the Doppler velocities by a factor of 10 to 100. At this point, we can measure this velocity with our instruments, and I'll see if I can get this about right. Yeah, about that. About a centimeter per second. So with that, I think I'll stop.
Thank you. Good job leaving time for questions. Does anybody have any questions?
I didn't think so.
Okay, well, thank you again. Who's next? I think it's Dr. Manson. Yes. Warn you when you have 1 minute.
Is there something to change the slides?
No.
So I stand over here and do it? Okay.
Stand right over there. Stand over there.
No, that'll work. The arrow down? Yeah, okay. Okay, we look at much smaller things. And even though they're much smaller, we have no trouble finding them, unlike the astronomers. We know where they are. However, characterizing them and learning something about them is tough because they're so little. And one of the main ways that we use to probe what's going on in atoms and molecules is with light and photons, basically. because the photons are a rather gentle touch. And so you learn things about the target. You know, if you smash something big into them, you have to understand the interaction as well as the target. So this is what we do. And these are theoretical studies. We do not get our hands dirty. We get carpal tunnel syndrome from working on the computer, but we have very clean carpal tunnel hands. And so what we really do is, you know that the microscopic world is governed by the Schrodinger equation, or if you want to be fancy, the Dirac equation, you know, relativistically. And we try to solve these equations. Unfortunately, we don't know how to solve them exactly, except in the simplest cases, because these are partial differential equations. We know two ways of solving partial differential equations. One of them is separation of variables. The other one is guessing. And if you can't do it either of those two ways, you gotta improvise. You have to approximate. And that's where being a scientist comes in. How do you put in the essential physics of a given situation? And how do you know that you've done it? Well, ultimately, as is written here, the yardstick for assessing the results is comparison with experiment. Although experiment is sometimes wrong also. No, never mind that. And so what we try to do, we predict phenomena and try to get the experimentalists to measure them. And sometimes things are measured and the experimentalists say, why is this like it is? And we try to explain that. And I'll show you a couple of examples. This is kind of a nice one, because the little white circles with the error bars, those are experimental measurements. The solid lines are the theory. Theorists do not make errors, so there's no error bars, as you know, right? Look, there it is in black and blue and white. The point is here, it was thought for a long time that this line, never mind exactly what it is, it's the ratio of two different ionization probabilities. And theoretically, it was thought that it should be 1.5 and constant, not change with energy. Well, it wasn't. And so I talked to this experimentalist who I met at a meeting, and he said, do you know what this is? And I said, I think so. We did a calculation, and the agreement was almost unbelievable. Because there it is. There's two separate calculations here, but it goes through all of the error bars. And we didn't fudge it. There were no adjustable parameters. This is what the results gave. So we were pretty sure that we understood all of the important physics in that. And there's other examples of this sort of thing. This is something, it's called the beta parameter. It has to do with the angular distribution of the photoelectrons. You know, when this is the photoelectric effect. A photon comes in, knocks out an electron. You can look at the angle that it comes out in predominantly. You measure this, and the asymmetry parameter is called the beta. And they had measured a bunch of these, and they couldn't, and the previous theory, whoops, that's not what I wanted. I think I wanted this. No? That's what I wanted, yeah. The previous theory did this. And this is what they measured up to this point. And we calculated, and we got that. And they said, you just got that because you knew our points. We're going to measure a really good point. And they measured this last point here. You see smaller error bars, and it still went through our theory. Okay, so what that means is that, at least in these two cases, we understood the basic physics involved. And there are a number of other situations that we look at. One of the coolest ones is something called attosecond time delay. They have found that in different processes, you can measure the time difference between them. And this time difference turns out to be of the order of attoseconds. That's really, really small. To give you an idea, it takes about tens of attoseconds for an electron in the ground state of the hydrogen atom to make one circuit. And they did some measurements, and we did some calculations, and, well, the measurements aren't great. The calculations are so-so. But these are the measurements here. If I can find, yeah. And these are the calculations. So we think we understand, at least qualitatively, what's going on there. And again, We can solve these equations exactly, so we have to approximate. And the skill in this business is not writing programs to solve coupled integral partial differential equations. The skill is understanding what physical effects to include. I'll stop here. Thank you.
Questions? Okay. If not, thank you again. We'll have time at the end to chat, I guess. All right. Oh, did you steal the clicker? You want me to? Oh, okay. Good. All right. Am I going the wrong way? Am I going backwards or no? These were all this. Oh, okay, that was just a preview of what Steve didn't get to show you. Okay, so it's my turn now. Okay, so I will be speaking on behalf of the nuclear physics group with a little emphasis on my favorite part of what we do in the group. So the nuclear physics group includes myself, Dr. Ha, and Dr. Sarsauer for faculty. There's also Brant Johnson, if you've had the chance to meet him. And we also have a postdoc, Shu, and Corolla also likes to dabble with our detectors a bit. We've had a number of grad students in the past year and several undergrads, especially if you were around over the summer, you saw all the work that the undergrads were involved in. I realize nobody's keeping time, so someone can, okay. So the nuclear physics group, we have sort of, the main overarching focus of understanding nuclear physics is really understanding the building blocks of nuclear matter, right? So what everything is made out of. And so the way we in our group try to study this is we go to the highest energies and slam particles together and understand what comes out of those collisions. So for many years, we were all involved in the Phoenix detector up at the Relativistic Heavy Ion Collider in New York. I'll show you in the next slide. However, we're in the process of transforming this detector into a new state-of-the-art detector, which will give us even more precise measurements, which we call S-Phoenix. And longer term, we have interest in what's called the electron-ion collider, which is really trying to understand the properties of the proton itself. In addition to that, other members in our group have worked on cosmic ray detection. Dr. Ha gave a presentation, a poster on that last week. Dr. Sarsauer is also comes from the low energy nuclear community where they've studied more on the weak force, whereas these studies focus on the strong force. And he also presented a poster last week. So specifically in these heavy ion collisions that we do at RIC, what we're trying to actually understand is the building blocks of matter. And so protons and neutrons aren't fundamental particles, right? They contain quarks and gluons. And so if you turn up the temperature and density high enough, you can actually get those quarks and gluons to behave like free particles, whereas normally they're confined into these protons and neutrons. And sort of this state is called a quark-gluon plasma, and this is what we believe the earliest universe was like immediately after the Big Bang. And we can recreate this by slamming gold nuclei into each other at relativistic speeds. We can create this same sort of environment to produce a quark-gluon plasma. And then the particles freeze out and come out to our detectors where we can actually measure them. So there's two places in the entire world that we can actually do this. One I've already mentioned is RIC up on Long Island. That's where our group is focused. However, there's also the Large Hadron Collider, probably most well known for discovering the Higgs particle. But in addition to that, they also study this quark-gluon plasma in lead-lead collisions. Okay. So as I said, we've wrapped up things with Phoenix. Because we want to be able to do state-of-the-art measurements. Specifically, we're looking at something called jets, so collimated sprays of particles, very similar to things that have been studied at the LHC, but they're in a very different energy regime than we are. So we've created this new detector system called S-Phoenix, and so this was like I said, born out of the fact that we wanted to do these jet-type measurements, and one of the detectors in this system is called the hadronic calorimeter. And so As some of you may have seen at the beginning of the summer, there was a hallway downstairs that was full of these boxes. Those boxes were full of tiles that were then tested by this team of grad students and undergrads over the summer. And so now the hallway looks like this. However, it won't be for long because we're going to be continuing to receive tiles. So over the summer, we had the first 1,500 of them, but there's about 6,000 more on their way. And so once these tiles were tested at here on the desktops downstairs in our lab, they were shipped off to Brookhaven to be inserted into the steel plates that you see here. And so this is the first completed sector up at Brookhaven Lab. So this thing is actually coming together. And then this is just about the electron-ion collider, which is a long-term future. We have people involved in the R&D for that. And students also have been very involved in the cosmic ray detectors. I don't know what happened in this picture. It's a beautiful picture of the group. Yeah, I don't know. It looks fine on my computer. Anyways, so here's a picture of actual people from our collaboration of S Phoenix when we had a collaboration meeting here. So here's our group website and the email addresses of the professors in the group. Thank you. Any questions? Okay. All right, so we'll leave questions, I guess, for the end. That works too. Okay. So who's next? That would be Pete.
All right, so these are the 5 areas that I work on. Which one do you want to hear about? All right, let's start with the astroinformatics cluster. Can you push that button? There, that one there. No, wrong.
It's not on
Oh.
It's on this.
Oh, it's over there. All right, let's do this. So what you're looking at is a chronograph. The sun is blocked out in the middle, and you see stuff is coming out all the time. This is the month of May 1998. And these things are dangerous when they come to us. Therefore, if we go to the next slide, if that works, yep. This is the same thing, but now it's coming straight at us. And they can do a lot of damage. This is what we study. The damage that's possible from these eruptions from the sun. And other stars have similar eruptions, and younger stars have even way larger eruptions than what the sun does. The sun is pretty mediocre. This is what the solar corona looks like, close up. Ooh, that's a horrible picture on the screen. Never mind. Magnetic fields and high temperature plasma. And what you're seeing here is what is called a magnetogram. White is magnetic field lines coming in, black is magnetic field lines coming out, and in between is what you have what we call a polarity inversion line. Is there a mouse with this thing?
Yeah, I moved it out front to make it easier.
Thank you. See if it wants to work. Yeah. Okay, so this is the evolution of the magnetic field, and which it won't do. Oh well. The polarity inversion line is interesting, but because it gives you an indication we found of the likelihood of a flare. If you calculate the fractal dimension of that line, the better the fractal dimension, the more likely a flare is. So these solar storms, these things that come straight at us, they threaten astronauts and spacecraft with high energy particles. They make necessary rerouting of airlines' polar routes, also for the particles. They distort radio signal and GPS, and most importantly, not yet, they damage communication satellites, and they induce geometrically induced currents. And this is the biggest danger, probably. Those currents go over the power grid. We have a big eruption that hits the Earth. A worst case analysis was made on the indication of President Bush and then followed up by President Obama. The worst that could happen is like the 1906 San Francisco earthquake, is that the entire power grid of the United States would be down for a couple of months. Now mention living in Atlanta and having no power for a couple of months. Best thing you can do is get in your car and get the hell out of here because your car will still work. No elevators, no air conditioning, no fridge, no light, no MARTA, nothing, no street lights. And that for a couple of months over the entire United States. So it is worth spending some money trying to predict these events because you can take protective measures. And it is worth studying them so you can make predictions. And that's where we come in. Our group here has received quite a bit of money from NASA directly now to study this. And we didn't even have to write a proposal. They just come at us, give us the money, and said, do the work. This is the other thing we're focusing on now. You get high energy particles coming out of the sun with these eruptions, and those can kill astronauts in principle. And since we're going to Mars and back to the moon, we want to predict those and take measures. So that was us. This is our group. This is the astroinformatics group. So this is computer scientists and physicists, astronomers working together. And I took Stuart in there because our work is very intertwined with that of the imaging group. And so you see Jane is part of that there. She looks at the interior of the sun. We've been growing very rapidly because we were founded in 2014. And what we're doing is, and that will be my last slide, and I'll put this online and you can just click and see it, the different subjects you want to see. Solar event prediction is now the key thing. So we want to develop benchmark data sets. That's what computer scientists insist upon. Apply cutting-edge machine learning technique to forecast flares. We do solar cycle prediction, which is actually by simulations, data-driven MHD forecast. And we're looking with Chara and Lowell Observatory to look at stars like the sun to learn more about the sun. So we want to see stars like the sun, but later or earlier in their life with different rotation rates. And we do content-based image recognition. So that's feature recognition without labels. If you look at Google and you see feature recognition of, say, the Eiffel Tower, usually that is because there is a subscript Eiffel Tower under there. Actually, the software doesn't know how to recognize the Eiffel Tower when it sees it. It's really difficult, actually. So we are looking at feature recognition without labels. That's called content-based. And tracking. The short-term focus is solar flare prediction, and then I want to move out to look at other stars, because there's an incredible amount of really good data coming in with Gaia, TESS, and Plato. And we're also, that's Rafal's contribution, he's branching out into medical and biological research. So we want to go in very different directions and do that. And that, I'll leave it at that.
Great. Thank you. Any questions for Dr. Martins? Where are we in the solar cycle right now?
I think just at the minimum, right? Yeah. Yeah. Don't worry, it'll come back.
Any other questions?
Yeah.
No? Okay, if not, let's thank you.
Thank you.
Hold it.
Presentation is actually a movie. So how do you want to do this? So I can close out of this, and then it's here. So however you want to start it. Okay?
Thank you. So I think this kind of a short. Yes, I'm Wei Chun Jiao. So the picture on the first slides, I don't know where you find that picture. That's where do you find my picture?
On your website.
My website? Really? I don't think. Okay, all right. I don't even know I have that picture on my website. Okay, anyway. So I think listen to this kind of a research summary talks is kind of a, you're watching news, right? News update really fast, right? It's a very short news. You got to absorb everything. I don't know how much have you absorbed it, but I think now we need to go to commercial. commercial break. But I guarantee you, you will not hear anything about like diabetes or psoriasis or lowering your cholesterol. Hopefully this will have a sound. So let me... Do you hear anything? Nope. That's weird. Okay, as you can tell, our group's called RECONS, Research Consortium on Nearby Stars. Basically, we research anything with nearby stars. So those folks you see that are our team members. So first is, I start from the youngest one, is Andrew, all right? And he just got back from Chile. So, and hopefully he has converted his jet lag. So it's been like 2 weeks, right? Okay. So basically, his research is to try to study the stellar's variability because we have a long-term data on nearby stars. So he tried to figure out, especially how stars varies in the long term, because like the TASS missions or Kepler missions are mainly focus on short-term variability. And our group have a very long-term data, so we can research that part. No one can touch that. And also, we take advantage of the Gaia missions, and he can find the stars with, we call it twin, basically almost identical on the HR diagram. So he can study how are they really identical in terms of variability. And Hodari, his main research is on young K-dwarfs. Speaking of a K-dwarf project, I think this project we started by accident, because when we plot all the nearby non-exoplanets, as of today, we realize a lot of the exoplanets either, mainly G-dwarfs, they are solar type stars, or some around the M's, but nothing around K-dwarfs. So when we plot that thing, we say, oh, someone has to go after those. So then Leo and Dan, they both will tackle the exoplanets around K-dwarfs. So Leo's project is mainly focused on the radial velocities, and we're using a CTL 1.5 meter Chiron to measure the radial velocity. And Dan will focus on the wide binaries, so we want to know the multiplicity for those K-dwarfs. And at the same time, Hodari will use the Chiron data to high-resolution spectrograph to study the young K-dwarfs' activity. And as for me, you already heard my talk last year, so I don't need to mention it again. So basically, mainly about nearby stars and nearby kid subgroups. And Todd, I don't know what he's doing. Right now he's somewhere in Alaska on a cruise ship. So I think that's basically about this group's research. Thank you.
Thank you. Any questions for Dr. Zhao?
I don't know. How many times I've done this, right? So I don't know who's the boss now.
What's the age of the youngest star within 25 parsecs?
Youngest star. Youngest star within 25 parsecs. I have no idea. I don't know. Does anyone know? What's the youngest star? Yeah, I don't recall. I know within 25 parsecs there are 300 entries. I don't know which one is the youngest.
Any other questions? Okay, if not, let's thank you. And so your presentation reminded me of another thing I forgot to bring up during the slides, was that for those students that participated in the poster session last week, I want to thank you again. You did a fantastic job. It seemed very like a lot of lively discussions. As you recall, I have people fill out a little survey thing. And so Murad and I just pulled one out of the stack, and that was actually Andrew that got that. So here's your super fancy erasable highlighter from GSU. So thank you. And so that wraps up all the talks that we had.